Today we're going to talk about cyclical changes in Earth's climate that have caused glaciers to form on continents over geologic time. There have been many times in geologic history where large glaciers have covered much of the land, and we recognize that, we know that, because glaciers leave distinctive scars on the land. This graph shows these large shifts going back in time, from time when there was no ice on Earth, which we might call a greenhouse Earth, to times that there were ice at the poles and over sometimes large bits of continent. These big fluctuations between an ice house and a greenhouse Earth are caused by two things: the position of continents and the circulation patterns of oceans. We're going to take a look at icehouse conditions 440 and 300 million years ago, and then at this latest cooling, the Pleistocene glacial period that we are in today. 400 million years ago, during the early Devonian, this is what the continents looked like. They were largely focused along the South Pole, with a few continental masses near the equator. Now remember that ocean currents flow towards the west along the equator, and they will be deflected when they encounter land masses, in this case bringing moisture to the South Pole, where it will fall as snow over continents and build glaciers. Another ice age period happened during the Pennsylvanian 300 million years ago. This is where, again, we see large continental masses along the South Pole, and you can see the South Pole Glacier fairly large in this diagram. By the way, future North America is right there in the middle, at the equator and a little bit north, which is a perfect climate for building forests and swamps, which will later become piles of dead plants, which will later become coal, in what will later become Pennsylvania. Now, this is what the continents looked like just 20 million years ago. Pangaea, the large supercontinent of all land masses, began to break up shortly after that last map I showed you, and by 20 million years ago, the map looked quite similar to what it is today, but not exactly the same. There are two significant differences. The first one is here in the Southern Ocean. You can see that the last connection between South America and Antarctica has recently broken, and that's really significant because now the Southern Ocean current can go all the way around the globe, isolating and helping to refrigerate Antarctica. The Antarctic ice sheet is beginning to form, and Earth is headed towards another cold period. The second significant difference is right here, between North and South America. This gap in the land is about to close, and the connection between the Atlantic and the Pacific Oceans will close up. And that means that gyres will form, as we've seen, in the North Atlantic and in the Pacific Ocean. That will bring warm, moist air in the Atlantic along the coast of North America and up to Greenland and Iceland, where it will precipitate out as snow and form the glaciers and the Arctic ice cap that we see today. Now, what is the difference between these big-scale continental mass and ocean-controlled icehouse and greenhouse Earths and the Milankovitch cycles we've just been looking at? Well, the main difference is scale. These large-scale changes that are formed by continents and ocean patterns are imprinted upon by a much smaller scale variation of the Milankovitch cycles. Remember, the Milankovitch cycles operate on a 100,000-year cyclical pattern, and they change temperature about 12-14 degrees between the cooler and the warmer of the Milankovitch cycles, but that's imprinted on this much larger cycle of global cooling and warming. So lately, where it's been in a cool Earth, this temperature fluctuation takes us between glacial periods and interglacial periods, where the amount of ice on the Earth waxes and wanes. Do you know what that means, waxes and wanes? It means to grow and to shrink. So we have ice all through this period, but the amount of ice at the poles and on continents has grown and shrunk over this last glacial period. These same Milankovitch cycles, however, were around back in the Cretaceous too, the last really long warm period we had. And the temperature also varied, probably 12-14 degrees between warm and cool cycles there. There just wasn't any ice around to record it. So, what causes ice to grow and shrink during these periods? This gets us back again to looking at feedback loops, and let's just reiterate the difference between a positive and a negative feedback loop. A positive feedback loop reinforces and exacerbates the original change. So here's an example of a positive feedback loop involving moisture in the atmosphere. You increase temperature a little bit, and that increases evaporation in the oceans, puts more water vapor in the atmosphere. Water is a greenhouse gas, so we have an enhanced greenhouse effect, which helps increase temperature slightly, which puts more water in the atmosphere, which leads to an enhanced greenhouse effect. So a positive feedback loop. Of course, there's a limit on this one because there's a limit to the amount of water vapor the air can hold. A negative feedback loop has a balancing effect, and evaporation tends to do this more commonly. The surface temperature is increased a little bit. That causes more evaporation from the oceans, which puts clouds in the atmosphere, which reflect the sunlight back into space, so there's less heat absorbed, and so temperature decreases slightly. So a negative feedback loop brings the temperature back into balance. The most important feedback loop for ice is the albedo feedback loop, and albedo is a positive feedback loop. What is albedo? One of your vocabulary words, so you should know this. Albedo is the reflective effect of ice and snow, and it causes a positive feedback loop whether it's helping to grow glaciers or to shrink them. So let's look at the right first. Moving into a cooler Earth situation, temperature decreases, ice forms. That ice reflects solar radiation, making the temperature even cooler, making a more compatible situation for more ice to form, which causes more reflection, which cools things off, which causes more ice. A positive feedback loop leading to bigger glaciers. The same thing can happen if you start to shrink the glaciers for one reason or another. So ice melts, you end up around the glaciers with either more ocean water or more land that absorbs more temperature than ice does, less reflection. So that allows temperature to increase some more, which melts the ice some more, which allows for more absorption of heat, less reflection, which elevates temperature more, which causes more ice to melt. Either way, whether you're building glaciers or breaking them down, the albedo effect is a positive feedback loop. And once it gets going, it tends to accelerate the effect in one direction or another.